Hello, my name is Jerry Lowe. I'm the Head of Technology for Advertising and Marketing Solutions at AWS. Welcome to the AdTech track at reInvent. The following case study will show you how to construct a data pipeline that processes 2.9 million events per second. That is, 250 billion events per day. In the next 28 minutes, Ofer and Yair will share their experience building this magnificent beast at the Nielsen data pipeline. As always, your feedback is important. Please click on the CSAT survey at the end of this presentation, and if you like it, a high CSAT score allows us to come back next year. A big thank you to Ofer and Yair.
Thank you, Jerry. Let's start by explaining what serverless is. So with serverless, you could write some code and then run it automatically on the serverless infrastructure without having to manage servers or deploy or update them. The main benefits are that you only pay for what you use. So when your code terminates, you stop paying for it, and you get automatic scale. And the reason is you can invoke your code many times, and that's a great way to scale your system. Serverless is great. You can create all kinds of small scripts. It's very useful. A lot of people use it to automate all kinds of DevOps processes. And you can even connect a few scripts into small state machines, which is awesome. But can you build huge systems with it? Can you build something like this? Will it even work? So in this talk, we're going to tell you about a system that we've built that does exactly that. We call it data out, and it processes up to 250 billion events a day. And the nice thing about it, it's running on serverless. We did a really nice video with Amazon. This is my architecture video series. And if you'd like to watch it, you could watch it at the link below, bit.ly/TMA serverless. So in this talk, we're going to show you how to build such a system, and we're going to do it right now. We'll start by explaining the ad industry problems we set out to solve. We'll tell you why serverless is such a great solution. We'll go over a few pitfalls we tackled and how we solved them. And I think you'll conclude you can build it as well. Before we start, I want to present ourselves. My name is Ofer Dubrovsky. I'm a big data dev lead, and I think serverless is the revolution. And with me is Yair Reuveni. Yair?
I'm leading the data engineering group in the Nielsen Marketing Cloud. And my motto is, when you build a platform, never be the bottleneck.
Okay, so before we go on, I want to give you some background about what we do. So we are called Nielsen Marketing Cloud. We are a data management platform, DMP for short. The system was acquired from a startup in 2015, and ever since we've been developing it. We build marketing segments and device graphs, and this is really useful for marketers. They could use this data to run campaigns and make business decisions. In a nutshell, we're cloud native. We process about 60 terabytes of new data every day and store about 5 petabytes total. We're heavy users of Spark. We run lots of Spark clusters. And as you will see, we're heavy users of Lambda, serverless Lambda functions. In a typical day, we invoke about 6 million of them. The DMP problem we set out to solve is the following. We create segments. Segments are basically a group of IDs and a label. IDs are device IDs or user IDs, and a label could be pizza or cycling or anything you'd like. This is pretty much like a mailing list. If you're a pizzeria and you have a mailing list, you could send coupons to your customers. Marketers do the same with these groups of segments. They could run campaigns to a segment or a combination of segments, and they love it. The DMP constantly creates new segments and adds IDs to the existing segments. And then we have to upload it to all our ad platforms so marketers can use them. For every segment and device pair we create, we usually create lots of events because we need to upload it to many of our ad platform partners, all the ones that ask for this data. Until it's loaded to the app platforms, the marketers can't use it, but once it's uploaded, they could use it to run campaigns. Let's look at the challenges we had when building this system. So on the one hand, we had to tackle the transform. We partner with about 140 platforms, and we have close to 600 accounts on them, each one requiring a different data transformation. On the dispatch side, we dispatch a huge amount of data, so we had to tackle that as well. If we look at the items we set out to solve, they're the following. On the transform, obviously we had scale as a big issue, but also quick integrations. Because we have so many partners and we constantly add more, we wanted this to be really quick and easy. On the dispatch side, especially because this is going over the internet and is a bit slower, we had to tackle scale and bursts of data, and it had to be at an affordable cost. If it was not cost effective, just because the sheer scale, this would have been very expensive to run. And to tell you all about it and how we ended up tackling these problems, I'm going to pass it on to Yar, who'll explain it all. Yar?
Thank you, Ofer. Okay, so transform and dispatch. Let's see how we solved it. Let's take a look at our system architecture at a high level. As Ofer has explained, our DMP is generating segments. These arrive in files, which are basically our incoming tasks. And then in the first phase of the system, we need to take those segments and perform the various transformations required by the different integrations, by the 600 different integrations we have. And then in the second phase of the system, we need to take the transform data and perform the actual data delivery to the different endpoints and partners we are integrating with. Okay, let's take a dive into each of the sides of the flow and see how it's implemented. And let's start with the dispatch side of the flow. So for dispatch, we had two main challenges. First and foremost, it's the scale and the burstiness nature of our data. Second, we wanted to achieve this in an affordable cost that does not increase dramatically as we add more data. When you look at our system in the numbers, on a typical day, we're processing over 100 billion events. On a top day ever, we process 250 billion events coming in 17 million files with a total of 55 terabytes. Moreover, when you look at the way our data scales up and down throughout the day, it varies by a factor of 6, so somewhere between around 1 terabyte in the low hours of the day up to 6 terabytes at the peak hours of the day. So definitely incredible scale, huge volumes, and we were looking for an elegant and simple solution to tackle this. Now, serverless is just perfect for this. If you think about the dispatch action, it's relatively easy to isolate, and it's a great fit for this execution model. But let's see how great serverless is. Now, when you look at classical systems, they're usually built for the worst case. You set up enough resources and infrastructure in order to handle the normal load and the rush hour. But then, many hours are just like this. And what you end up with is a lot of those servers sitting down, doing nothing, idling away, and just wasting money. Now, in a data processing pipeline, in the classical model, the way it goes is data comes in over time, and you usually set up some preset cluster size with enough resources to be able to handle the traffic that's coming in. And then most of the time is just idle time, servers sitting idle and doing nothing. And then sometimes you get one of those unexpected loads. And then like with a congested highway, when there's some unexpected traffic coming in, what you end up with is a traffic jam. Same goes here. Internal queues get overloaded and sometimes even spill over. Internal components get stuck. Sometimes you need to manually intervene in order to get the system running again, and you end up with delays. So all in all, in the classical model, you end up with excessive costs, and sometimes delays. Now in the serverless approach, as data comes in over time, you can just spin up resources as many as you need in order to handle the traffic. And then your processing is perfectly aligned with the demand. And then comparing to the classical model, the rest of the time is just pure savings. Now another cool fact about serverless, since it's an isolated compute action, any improvement you introduce to your code can immediately be translated into cost reductions. Now, let's take another look at our high-level system again, high-level architecture again. We set off to explain how we solve the dispatch side of the system, and we chose AWS Lambda for that. Let's see how it's implemented. So our transform data comes in as tasks in our RDS management database. And then we have a work manager Lambda that arranges those tasks and prepares them for the dispatch. And then we're using a fan-out architecture where the work manager invokes dispatcher lambdas in order to handle, to comply with the demand. So as more traffic comes in, the work manager just invokes more and more of those dispatch lambdas, and they take the traffic and handle it. The dispatch lambdas, they take their input from an S3 bucket and perform the actual delivery. We support several delivery methods like HTTP or file transfer. And if you remember, we had a challenge with burst. So this fan-out architecture is actually amazing for solving the burst problem. So if a burst comes in, the work manager just invokes more and more of the dispatcher lambdas up to the max capacity of concurrent invocations we can run. And then we can handle any incoming burst quickly and immediately. Now, when you look at our daily Lambda invocation over time, you can see how our data varies between the days. On a typical day, we're processing somewhere between 4 to 6 million Lambda invocations. And our top day ever, we topped around 17 million Lambda invocations. Now, if you look at the way our data scales up and down throughout the day, in this example, this is one of our largest accounts. You can see how it scales from around 600 gigabytes per hour in the low times of the day up to 1.5 terabytes at the peak hours of the day. And the way we implemented our dispatch side of the system is just scaling to demand exactly like we wanted it. Okay, let's talk about our second challenge, and that's the transform side of the system. So again, for transform, we had two main challenges to solve for. The first one was scale, and here it comes with additional aspects. Since we have around 600 different transformations, and some of them are for large accounts, some of them are for small accounts, our scaling problem also comes with a big skew problem. And the second one was quick integrations. Since we have so many integrations, we wanted a way to quickly add more and more integrations without requiring R&D. So let's see how we solve these challenges. Let's take another look at our high-level architecture. We talked about how we solved the dispatch side of the system using that fan-out architecture with AWS Lambda. For the transform side of the system, we chose to use Spark SQL. We are using standalone isolated Spark nodes because we wanted to solve this in the serverless approach. So let's see how we implemented the transform side, and we are running Spark in the serverless model. So we are running those standalone isolated Spark nodes on a Kubernetes cluster. We are using EKS, which is the Amazon managed Kubernetes service. And this allows us to spin the Spark pods up and down according to the demand. Our tasks come in an Amazon SQ, and the tasks are basically lists of files and the type of transformations required to be done on them. And then the pods, they pick up a task from the queue, they take their input data from the S3 bucket, perform the required transformation, and output their results to an intermediate S3 bucket that is later used by the dispatch phase. Now, again, in this side of the architecture, we also have a work manager Lambda that is listening to the incoming tasks we have in an RDS management database. These are basically those segments generated by our DMP. And our work manager here is the component that allows us to control our processing strategy in the transformer. So choosing how many bytes or events or files we have per task. Now, as for autoscaling, we are using two autoscaling layers in Kubernetes. We are using the horizontal pod autoscaler for spinning the Spark pods up and down. And we're using the cluster autoscaler to control how the cluster EC2 nodes scale. Okay, let's take a look at our autoscaling in action. The important thing about autoscaling is choosing the right metric to scale upon. And we are using the number of tasks we have in our SQS. And you can see on the top, in this example, you can see how our tasks are coming in over time. And on the bottom, you can see how our cluster is perfectly aligned with the amount of tasks coming in the queue. So when the tasks go up, the cluster just adds more Spark pods. And when the tasks go down, the cluster just removes the unnecessary pods. And when you look at the bottom part, you can also see how the cluster adds EC2 nodes to the cluster when they are required, when we have more live nodes, and it takes them down when we no longer need them. So no servers with idle time, and we are scaling to demand exactly like we wanted it. Now, remember the bursts problem? Here we also pretty elegantly handle bursts. So you can see in this example, we got a very big burst, a few hundred tasks coming in a very short period of time. And you can see how our cluster immediately spun up all the required Spark pods to comply with this backlog. And you can see how the moment the backlog got completed, the cluster brought down the resources and everything went back to normal. Now, let's look at our scaling efficiency. So it's pretty good. You can see it's a flat line, relatively a flat line, which means as we add more and more instances, we pretty much keep the same amount of throughput per instance. And in a previous solution we had in this part of the system, we used to have a Spark cluster running on EMR. And it actually suffered from those classical model problems. If you recall, we have around 600 different transformations and a very big skew problem. And in cases where we had a large backlog coming in, this actually had a very big problem coping with it. And many times we found ourselves needing to run multiple clusters in parallel in order to be able to handle the load. So if you compare the previous solution with the new solution, you can actually see how in the previous solution, it didn't have this flat line of efficiency as we added more instances. So as we added more instances to the Spark cluster, we had a decline in the amount of throughput per instance we add. We actually reached a glass ceiling around 13 instances. From that point on, when we added more instances, it didn't have a significant enough effect, which led us to run multiple clusters. Now, when you compare on an instance per instance basis, you can see that the new solution actually utilizes the resources much better, and we achieve an almost 2.5 times better utilization, which leads to much better throughput in the overall system, and it also affects the costs. Now, comparing the cost in the previous solution, we pretty much had a constant cost throughout time, over time, for this cluster that was running. And in the new solution, our costs go up and down according to the amount of traffic we process every day. So comparing the solutions with the new solution, the rest of the time is just pure savings. Doing this change, we managed to reduce our cost by 55%, which led to a $15,000 cost reduction yearly. Okay, another thing we set up to solve was the codeless transformations. So actually, in this part of the system, we in the R&D, we were a very big bottleneck in the process because every new integration that required us to introduce additional code changes, it would take us weeks to add those new integrations. So we were looking for a way to solve this in a way that's going to be shorter and from configuration. The concept we came with is to use Spark SQL. And the reason is basically using plain SQL, you could pretty much define most of the configurations required on our data. And then for those custom special cases, you could always use the rich library of functions that comes with the Spark API. So choosing Spark SQL, we managed to solve this using directly from configuration. And let's see an example. So here's an example of one of our transformation configurations. We have this concept of operators. And you can see in blue, these are these Spark custom operators. We use those kind of operators for things like loading the files, decoding them, or choosing a specific output format. And in yellow, you can see the SQL operator. And you can see, you can basically, any kind of transformation you can define with plain SQL, you can configure this way. And our tech operations group, they use this to configure new integrations. So comparing the two solutions, in the previous solution, when we had to actually write code for every new integration we introduced, it sometimes took us weeks to add new integrations to the system, the development and testing. Now in the new solution, our tech operations group, all they have to do is just add within about 15 to 30 minutes, they add a new configuration to the config file, and then a couple hours of testing, that's it. And you have a new integration in production. And we're no longer a bottleneck at this part of the system. Okay, let's tie it all together. So this is our system at a high level, system architecture at a high level. We solved the dispatch side using AWS Lambda with the fan-out architecture. And we solved the transform side using those isolated Spark standalone nodes running on Kubernetes. And they are both running in the serverless approach. And all in all, the whole system turned up looking like this. You can see the transform side on the left with the Kubernetes cluster. And you can see the dispatch side on the right with the fan-out architecture. And in real life, not everything is just rosy and bright. And we actually faced a lot of hurdles and pitfalls along the way, building and operating this system in production. And I'll pass it on to Ofer to share with you all of the juicy details about a couple of interesting pitfalls we faced. Ofer?
Thank you, Yair. Let's talk about some problems we've hit along the road. And the first one, which is slightly surprising, is DDoS. On September 5, 2019, 10:45 a.m., we got an email from a partner, and it said the following. 2 weeks ago, an engineer flagged the incoming queries per second from your side to our API. This was so intense, our infrastructure was at a strain coping with it. We were practically flooding our partner's system. And if you recall, Yair said that we can handle pretty much any burst coming our way. We would just process it and send it along. But most systems don't work like this and may have a hard time dealing with flooding situations. We were practically running a DDoS attack. To solve this, we decided to implement a rate limiting mechanism. Data would come in on the left and we would limit it, and it would come out on the right, nice and easy and flow well and behaved. We created a system that allows you to select a strategy and apply it for each account. You set a period and the limitation you'd like to apply on it. A period could be anything, like from a second, a minute, 10 minutes, an hour. And the limitations we currently support are the following. Size, tasks. Task is the number of times we send data to the platform during that time, and the number of HTTP requests, which was a request from one of our partners. Let's see how it works in practice. Let's assume we have a size limit of 240 megabytes per minute. That works out to be 4 megabytes per second. Our work manager, which makes the dispatch decisions, wakes up roughly every 3 seconds. So, as you can see in front of you, we are sending 3 files, and at second 3, when the work manager wakes up, we are sending a total of 3 megabytes per second. If you recall, the limit we wanted was 4 megabytes per second. So we have 1 megabyte of free capacity we could use to send extra data. So it will initiate another file. In second 6, when it'll wake up, one of the files had already been completed. So we are down to 3 again. Again, it can initiate more data, and it will initiate another file, and so on and so on. Notice 2 things. One, we never go over the limit. We're always either at the limit we set or slightly below it, which is great. The second thing is that the work manager doesn't really need to wake up every set amount of time, but could basically wake up whenever it works, and that gives us a lot of flexibility in the system. There is one problem though. How do you determine the rate per second? We don't really know it. We know the file size, 40 megabytes, for example. To solve this, we've implemented another mechanism that would once an hour calculate statistics for every account over the last hours and calculate a formula from it that allows you to figure out how long it's going to take to send a file. Now, you have to realize this is different from platform to platform. It could vary over time because of network congestion, or platforms may upgrade their infrastructure, so long-term they may be able to process more. So let's look at an example. Let's say our file is 40 megabytes. We plug it into our formula. We get that it's going to estimated time to send the file is 2 minutes. That works out to be 1/3 of a megabyte per second, which is exactly the number our work manager needs to be able to make the dispatch decisions. Problem solved. Let's see how it works in practice. Before implementing this, we had a case where one of our partners asked us to limit the amount of data we send. So we didn't have the mechanism. We had to hardcode limit it to sending just single files every time. The utilization was pretty bad. It was 28%. After implementing this, our utilization shot up to 69%, which is 2.5 times more data over the same pipeline. And this is really critical because before, every time we got a burst, we could not really send all the data in some cases and had to drop some data. This is no longer a problem. So not only are we behaving nicely, we can send much more data through the same pipes. Let's look at the second problem we ran into, which was practically a bug, a reprocessing bug. So if you recall, the pods that Yar mentioned pick up tasks and transform the data. On average, it takes 15 to 20 minutes to run a transformation on a big chunk of data. So in case a pod terminates or gets stuck, we set a reprocess threshold, which means that if a task has not been completed for a very long time, we would set it to reprocess. And we set the reprocess threshold at 2 hours. What happened was we were working on a new version and testing all kinds of thresholds. And for some reason, we forgot to change the threshold back, and the threshold changed to a much lower number. As a result, a lot of tasks got marked to get reprocessed, even as they were processed correctly by the pods. So some tasks were completed and then set to reprocess and reprocess. Some of them ended up getting reprocessed 38 times. And this data then went to the dispatcher and would get sent 38 times to the partner platform. Obviously, that was very expensive and not a great situation to be in. The total cost we incurred from that was $3,400 from the time we deployed the code until we discovered and stopped it. And let's look at our solution. The solution was basically predicting task failures as they get processed. The way we did this is as follows. We added a heartbeat to the pods that would get sent every minute. This would get written to the database, and then we have a monitoring lambda that would check periodically all the tasks. If it finds a task that was missing a heartbeat for 3 consecutive minutes, it would mark it for reprocessing. Moreover, we also added a reprocess limit, so if a task gets processed more than 3 times, we would not reprocess it again. Both of these issues completely solved the problem, and what's even nicer, whereas before it could take us around 2 hours to reprocess a stuck task, this is no longer the case, and we almost immediately get it processed, reducing the average processing time significantly. All right, let's sum it up. So we started out by asking, can we build this? And I think we can definitely conclude that yes, we can. We can definitely build such a system. Not only that, it will have lots of great benefits. With serverless, you get great power, you can easily scale and handle crazy loads, and the nice thing about it, you only pay for what you use. This is great, and especially for us solving difficult ad industry problems, this is really a great technology. So, what is it going to be? You can choose the blue pill and stay with your classical systems, or take the red pill and go down the serverless rabbit hole. Thank you. If you'd like to get in touch with us, here are our details, and don't forget to rate our talk.